Hi everyone. So this is a presentation that I gave at the Blackhat MEA meetup just recently, and I am making a recording of this talk for the benefit of others who are interested in my talk but were not able to attend it. So this talk is titled "Classifying Packed Malware Using Machine Learning." A little bit of information about myself. My name is Carlo. I was a programmer for 10 years until I switched to cybersecurity. And I am now working as a level 2 SOC analyst and content engineer. Ever since I started, I wanted to make use of my development expertise in the field of cybersecurity. So this is my way of contributing to the community. If you're a malware analyst, you know that almost all malware out in the wild nowadays are now using some form of packer tool because it's easy to compress, encrypt, and obfuscate the code, which allows it to evade detection engines. And if you really want to find out what a malware is capable of, you are left with no choice but to run it and then inspect it using dynamic analysis. And sometimes knowing the packer tool that is used greatly helps a lot in properly analyzing a malware. And there are processes and tools that the community has developed to be able to detect and identify the packer that is used. Number one is the use of entropy, wherein it checks the amount of randomness in a program. Uh, while this works, it allows us to identify if a packer is encrypted. It doesn't really tell us the packer tool that is used. And this is where signatures comes in. Basically, there is a database of signatures that, like tools like Detect It Easy, they have a database wherein there are specific signatures that they try to look for in a file. Let's say a specific set of bytes or a specific set of strings that when they see it in a new file, they would be able to say that, okay, I saw this signature in a previous version of Empress or previous version of UPX, and I saw this in this one, and it will allow us to identify that this new file is a UPX packed malware. And this works for the most part, but it's not 100% accurate. And it is because that sometimes, um, well, sometimes the resulting executable uh, changes. There may be times when a signature is not present in one file, um, and sometimes whenever there are updates within the packer tools, it changes radically how it encrypts the data, meaning the signatures that you had before may not work anymore because it's already updated. Plus, malware authors can also modify their executables without changing how it works. So that means the so that means your signatures may not work as well. So to keep up with this, analysts need to always update their signatures in order to keep up. But there are thousands and thousands of new malware coming out, and not enough malware analysts who are updating the signatures. So it's really hard to keep up. And this is where an automated system would be really beneficial, right? Uh, and the solution, question mark, I feel is machine learning. With machine learning, it does not rely on signatures. What it relies on is patterns that it has learned from an existing data set that it has trained before. Later, I'll talk more about how it works. But for now, just try to understand that it can detect minute patterns so that even if there is a new update wherein let's say for example, specific bytes has moved quite a bit, the orientation has changed, the machine learning model can still and should still be able to see these small minute changes in patterns and still be able to see it. And since it's a machine learning model, we can also automate this process by having regular updates of the training data. So even if there are new versions of a packed malware, we can automatically download this malware and then train our model with this new data set. So now it can detect these new patterns. And we can do this constantly, maybe daily or weekly or monthly. This means there is no more need to manually update the signatures because our models can now automatically infer these patterns. But before we could fully appreciate that solution, let's talk a little bit about how machine learning works. Now, we kind of have an idea, right? Machine learning is about learning. But let's try to talk more about how it works. But keep in mind that the machine learning field is very vast. And this explanation is just a simplified version to give you an idea on how this solution works. So, machine learning is learning from data. So, we have a model wherein we give it data and it would try to look for patterns within that data so that it can be able to create, it can be able to do predictions. So, what it does is that it looks through this data multiple times, millions of times, constantly, and will try to look for these patterns that it needs. For example, in trying to determine how a sentence is constructed, we would have a model wherein we would give it lots and lots of written documents or written works, wherein after going through the data, it would be able to infer and it would be able to see, like for example, oh, wait a minute. The first letter of a sentence is always a capital letter. And then after a few set of words, eventually it ends with a period. And then after a period, it's a space. And after a space, it's another sentence. And what's great about this is that no one told it that this is the case. These are rules that we know that it learned just by looking at the data. And this is the power of machine learning, is that no need to program it, just give it all the data and it would be able to eventually get to know all of these rules that we have. And even if there are changes in the sentence construction, for example, maybe the sentence, we know that the sentence doesn't always end with a period. Sometimes it ends with a comma, or maybe there's no period at all. There's no punctuation at all. Maybe it ends with a exclamation point. So even if there are variations within these rules, it can still be able to see these patterns. It can be able to learn these patterns, which is great. And as for classifying packed malware, this is how it does this. So if you would look at this, what do you call this? This diagram at the bottom, here is what a visual representation of an original PE file would look like. There's a .text section, .data, resource section, and so on. If we pack this original file into, for example, an ASPack, this is what it would look like. If we pack it with UPX, it would look like this. Empress would be like this, and so on and so forth. And as humans, we could definitely see that there is a pattern. There is a pattern that we could see that differentiates how an Empress looks like with a UPX, how different it is with an ASPAC, and so on. And aside from that, if you as a human, if I give you 1,000 versions of ASPAC, 1,000 samples of ASPAC, eventually you'll be able to see a pattern. Okay, that if I give you another ASPAC, you could another ASPAC sample, you could say, oh yeah, I've seen that before. That is an ASPAC. Oh yeah, I've seen that. That's an Empress, right? And if we can do that, a machine learning model can do that as well, and much more effective and much more faster. Because and it is very effective that even if there are minute changes, really small changes, it can still be able to detect that even better than we can. So for example, if you could check here the Empress and UPX, from first glance, if you don't know the slight differences, like this one, like the Empress has a small sliver of orange over here, but the UPX doesn't have it, right? Even how small that portion is, a machine learning model can be able to detect that. Okay, so using all of that information, all of those things that I learned, I now decided that I wanted to create a prototype. And that prototype is this one. And I call it Vigilant. It stands for Visual Guided Learning for Neutralizing Threats. And what it does is that it converts executables into image representations. Let's say for each byte from 0 to 255 are then converted into a pixel here on the left, or here on the right, I'm sorry. And then these images that it creates are then fed into a machine learning model so that it can try to determine the pattern from all of these executables, from all of these image representation of these executables. And from here, it can now be able to predict the similarities as percentages. Okay, so that's how it works, and here is what it looks like. All right, so this is a tool that is now available online, which you could access at packers.vigilant.com. Keep note, it's number 4 in place of the A. And what it does is that you could just upload any file, any exe file, let's say for this one, and just press upload. And as I've mentioned before, what it would do is that it would convert that file into an image representation, and then it would then try to look for a pattern from within that image. So here it says, oh, from what I've seen, this file that you uploaded is 100% ASPAC. Now, that's a bit suspicious that it's 100%. It shouldn't be that way, but let's try another one. Let's say maybe a Themida. Oh, there you go. Oh, so this one is a good example. All right, so this random file, I know that it's Themida, or sorry, I downloaded it from the internet randomly, and a Yara rule was able to determine that this is a Themida, but we're not sure. So once I uploaded that one, it's now able to determine that these are the percentages from this one. So it's telling us that, well, 53.3% of the patterns that I see here are from others. I'm not sure what it is. But 42% I've seen from previous Themida samples that I've seen. Some of it are petite, some of it are NSPAC and amber, and so on and so forth. So this is a really great prediction. So it's not 100% sure what it is, right? But it definitely gives us a better idea. Okay, maybe it's 42% Themida. And after looking into that, you might wonder, why convert it to an image? Well, there has been a lot of improvements of in the field of machine learning lately, wherein a lot of the improvements has happened in the image recognition side of machine learning. Like like there like how in the self-driving cars, it can now detect like if it's a human, if it's a car, and so on, and that's because it can detect that in the form of an image. And we are just making use of existing algorithms so that we don't have to create our own. And these image algorithms are very, very, very good at detecting patterns on images. And another great thing is that it uses the GPU, or the graphics processing unit of our video cards. And with a faster GPU means faster training. That means we don't have to spend 24 hours to train a model. Now it just takes 1 hour to train uh, 10,000 images. And I've tried that. More GPU means, yeah, faster training. And another reason why I've converted into an image is that it makes it easy for me to manually verify if the dataset is correct. For example, if you would look at here as at this image right here, this is a GIF image of 1,000 versions of UPX that are looping. And you could see that definitely these 1,000 UPX files has a pattern that we could see. You could see that it changes somewhat. These are the garbled data. There's white right here. There's a green right here. Garbled data right here. But here on the very top, those are the headers. And there are certain parts of the headers that changes, but not too much. You could still see that there is a pattern over here. And here on the blue side as well, you could see that there is a pattern right here. Again, as humans, we can kind of see that those patterns, but machine learning models can be very, very good at detecting these patterns. All right. So as you've seen, there are current limitations with my implementation of this web app. Um, I mentioned that the accuracy of the model is only as accurate as the training data set. Meaning, if, for example, I train it with data, and let's say, for example, I want to train it to detect UPX, but I made a mistake. For example, I incorrectly added data from UPX, from a different category like Themida and Empress, along with the data set for UPX. That means if I feed that into the machine learning model, it would, well, it might incorrectly identify malware in the future because our data set is not clean. And this is actually one of the biggest um, challenges that I faced creating this application, which is trying to look for clean data set where I am sure that this data that I'm feeding it is definitely UPX. This data is definitely Empress. This one is definitely Themida. So I need to be very extra careful in what I feed my model because it definitely affects the accuracy of my training. Aside from that, another current limitations are the categories. You would notice that the percentages, it can only detect 10 different categories, so UPX and so on and so forth. And then if it aside from these, it would just be others. And this is because if this is a limitation of the hardware or the hardware that I have access to. If I want my model to be able to classify more packers, like 100 packers, I need to increase the amount of resources that I have. And more resources means more GPU, and more GPU means more cost, which I don't have the money for right now. So for now, I am limited to just the 10 because that's the only one that I can definitely afford. Which is why when it comes to machine learning, the big companies have their data centers full of GPUs because that is what you need if you want to train a model with lots and lots of data. And right now, I'm limited to just this one. But these limitations are actually solvable, right? So and hopefully in the future, once I continue more with this project, I can be able to overcome these limitations. So yes, there you have it. If you want to try out the tool, you could access it at packers@vigilant.com. And if you have any questions, comments, or suggestions, feel free to reach out to me on Twitter at accidentalrebel.com. That's it. Thank you very much.